Our next speaker is Starr D'Auria, and Ms. D'Auria is a non-destructive evaluation engineer at Extende Inc., where she specializes in CIVA simulations. Today, she's going to present CIVA NDT simulation, improving inspections today for a better tomorrow. Thank you very much. Oops. There we go.
Awesome. Thank you, Elizabeth.
Thank you.
I'm really excited to talk to you all today. I got the pleasure of meeting a couple of you already, and I look forward to meeting more of you later on today. But just to kind of intro to see where the audience is at in this topic, just that helps me know what to say, how to explain things. How many of you are familiar with non-destructive testing? And just so you can get some blood flowing, I want you to kind of like pop up, out of your seat and stand up. So how many of you are familiar with non-destructive testing? Yeah, stand up. Awesome. Great. So actually, you can all stand up because you all are actually familiar with it, but you just maybe don't know. So let's all stand up. Yay. Okay, cool. I just didn't want to be the only one standing. So thank you. So what non-destructive testing is, for those of you who are not sure that you actually already know what this is, who has ever broken a bone or knows someone who has broken a bone? Right, pretty much everybody. Oh, you guys don't want to stand up anymore. Okay, I see how this is. Okay. So when you went to the doctor, you most likely got an X-ray, and they were actually able to see whether or not you broke your bone by using X-ray technology. And this is what non-destructive testing is, because they didn't have to rip open your skin in order to look for that crack. So this is just one of the technologies that's used. Non-destructive testing is kind of self-explanatory, right? You're testing something without destroying it. And I'm just going to go through some of the benefits of using simulation in order to optimize inspections. But before we even get into that, I don't even think you guys need this definition. Just from today being here, you guys know what simulation is. And so we are going to look at how simulation will help us with our inspections. And so the first thing that you can do in industry, we know that we have the importance of making sure that everything that we're manufacturing is actually going to be reliable to keep people safe, to make sure that airplanes don't fall out of the sky, to make sure that our bridges don't crumble, to make sure that our ships and our sailors are okay. Right? You're laughing, but it's true. It's sad that sometimes this does happen. We want to make sure that people are safe, and we want to make sure that our testing is actually reliable. So you can use simulation to actually represent a real test and evaluate different scenarios to actually optimize on a certain inspection technique, compare different ones to make sure that you're actually able to find the different cracks or defects in materials before they go into service, or sometimes after having cyclic loading and fatigue stresses, that you're able to re-inspect it to see if those cracks have actually gotten worse or if they've emerged out of some type of defects in the material that you weren't able to see to begin with. And so simulation can help us to save time and money to ensure we're actually able to find what we need to find. The other thing that can be done, and I will explain this with an example. I was talking to a colleague of mine, and they had ordered a part, and there's something called ultrasonic testing. You guys are also familiar with this. So when women get pregnant, they go into the doctor, right? They get an ultrasound on their tummy to see the baby. We use the same technology, except for finding babies, we find cracks. So you can laugh. I thought that was hilarious. But anyways, so my colleague was doing ultrasonic scanning, and this component that they had, they weren't really familiar with the geometry. And so they were getting some interesting echoes, and they thought it was a defect. So they actually told the manufacturer they needed a new part. But what they realized after ordering the third part and waiting months and months and months and spending tons of money and man hours is that this echo actually was from geometry. So we can use simulation to model this kind of a component or more complex components and compare with experimental results and actually realize that these echoes we're finding and identify them as either geometry or something that we need to be concerned about. The next thing we can do is use it to qualify new procedures, new technologies. The keynote today, both of them were great, but the first one talked about not putting enough investment into newer technologies for testing. And that goes for non-destructive testing. We're very behind. There are a lot of new technologies. They're not being utilized in the field as much. And so you can use simulation software to be able to propose to your stakeholders that will actually give you the money to get these newer technologies, that we're able to save time by implementing new technologies, and we're still able to find what we need to find in order to make sure that people are safe, right? We're getting the criteria that we need from our customers. Everything's reliable and we can prove that. And this is kind of going into that part, right? Discuss those different conversations with technical stakeholders and convince them with images, which simulation can be very, very helpful with. And then something that I'm pretty passionate about is training the next generation. Simulation software, especially CIVA, is very visual, so you're able to use different images to quickly train up your new employees and help them understand what parameters, when you change them, like materials, and how that greatly affects the reliability of your inspections and the actual integrity of them. So I'm going to dig into not every type of non-destructive testing, but a couple of the different methods that are in CIVA. I'm not going to go through all of them just because there's actually quite a bit. So the first one we're going to cover is ultrasonic testing. We have our part and a probe. And what's going on here is we're simulating how the sound beam is actually propagating through the material to ensure that we are focusing in a good area. So let's see, I haven't tested this. So this blue area right here is where we have our max energy. So if there's a defect in that area, we're most likely to actually be able to recognize that and identify it, give it some sizing, figure out whether or not it's acceptable or rejectable according to acceptance criteria. But what's important here is sometimes your sound beam is going to change. We'll see this later on, and you'll actually have sound that's bouncing based on grain structures of your material, and you're not actually able to get a reliable scan. And so this is where simulation software is really important to do before you do that test. And so in the next image, this is a scanning coverage, basically seeing if you're actually able to cover that side of the weld to look for something like lack of fusion. So when it gets load bearing on it, that it doesn't rip apart. So here, once you've identified the geometry of your sound in your part and your material, then you're going to add different flaws, right? Because you want to make sure that not only am I covering the area of interest with sound, but I also am going to be able to find the relevant flaws I need to find. And sometimes these flaws are very, very, very small, especially in aerospace industries, because they have a lot of decisions to make in terms of weight and integrity of the material. And so they have to figure out what kind of size flaws they need to be able to find in order to keep the people safe, right, as they go through space. And so you can see in this example here that we're actually getting good responses and being able to detect these two flaws right here, but this one closer to the surface of this weld, we're not able to see very well. And so you would need to define a different technique or position your probe differently in order to actually find this indication. These are different components that you're able to simulate and evaluate min and max conditions. So different tolerances from your manufacturer that could definitely change your results of the integrity of your inspection, as well as different materials like we talked about. We'll look at some images. Here's just kind of an overview of all the different kind of flaws that you may be able to model, and you can get some pretty complex cracks that you're able to simulate as well. And then one thing you can use simulation software for is actually to decrease your man hours in the field by figuring out the different scanning steps that you have to do. So in UT, you have to overlap your probe to make sure you have good coverage. And so here you may be able to simulate different scanning steps to see if you can still get good coverage with shorter or with bigger increments, therefore decreasing the time that your inspectors have to inspect. This is super helpful when we get into submarines and aircraft carriers where these welds we're inspecting are just ginormous. And with pressure vessels, you have to do 100% UT, and that takes multiple days, especially with the older technologies that they're using. And so here we have different types of UT probes that can be used, different technologies, single element, dual element, phased arrays, just multiple elements, and they fire at a certain time in order to direct sound and focus in a certain area. here we have just a single element probe that is modeled with two different materials, and you can greatly see how this coarse grained specimen is actually scattering the noise. And so you want to make sure that this is not the case for your application, right? Because if it is, then when it goes into service, you may have a catastrophe, and that's going to cost people's lives, money, and time, right? And so we want to make sure this is not going to happen. And then here's another example where you may want to study the difference between different waves and different techniques. So here we have a shear wave, which is a type of wave that the UT can emit. And we can see here that the energy is being lost within the weld because of the grain structure. But if you change the technique or the wave type to longitudinal 45, then you actually have some really good coverage here. And so these are really good images that you can show your stakeholders. I need to use this. This is why. So here we have an application with some flaws in the same part. It's actually a really noisy material that we see in different materials that we use, like steel or stainless steel. And just simply changing the focusing or the geometry of the probe can actually greatly increase your ability to find the indications you need to find. And so we see here that with no focusing, our signal that we need to pick up is kind of buried within the noise of our part because it's being scattered. The second one, it gets a little better, but it's still not great. But then the third one, where some bifocal focusing was used, you can really easily distinguish between the noisiness of the material and the flaw. And this is really important to be able to simulate ahead of time. Now going into radiography, I met someone in here that actually has a background in this, so hopefully I don't mess it up. And if I do, you can let me know because I am normally UT and most people specialize in a certain method. But anyways, so for RT simulation, it's a similar concept. You want to figure out the optimal solutions, the optimal settings for your inspection. And so you're able to test different radiation sources and evaluate how radiation is scattering and how different filters can actually help you to get more energy through a component and onto your film. So if you guys are going to the doctor, right, to get an X-ray, moving this machine and they're trying to get it in a certain position, a certain distance, all those things greatly affect the image quality of the film. And so if you're someone in this industry, you may look and see like they have little tape in certain points because they've already done the calculations and they're just trying to quickly line it up. But you can't always do that on a ship or an airplane or a submarine. You have to do those calculations and really figure out with some more complex geometry and greater density materials how to propagate through that weld, for example. And so here is an example that Lehigh University was studying. They were studying an application where they needed to be able to find that defect in the wire in a steel anchorage inside of concrete. And so they were actually going to shoot through concrete in order to find this. And this was done actually in 2015 with simulation software. So imagine it's just gotten a lot better since then. And the first thing that they did was they made sure they had a good kV or energy source. And then they moved on from there and they tested different exposure times and how long, kind of, if you think about it, like you're baking in the sun, the longer you're there, the redder you turn, right? The more sunburned you get. It's kind of similar. So you can see as the exposure time increases, the film actually gets a lot darker. Similar concept. So they needed to find the best exposure time to where they could distinguish between the defect and the other components. So once they figured out that exposure time, then they added actually in some more complex material, so some aggregate into the concrete, and they were still able to actually find this defect. And then they knew that their technique was going to be reliable for what they needed to test. And this is something that if they would have had to do this without simulation, it would have taken a long time, whereas this took them a day. And then eddy current simulation. I don't have a great example in real life in the medical field for this, but there is one. I just don't know how to explain it very well. But anyways, you can test multiple different probes, similar concept to UT in order to find what you need. It just is used for more subsurface cracking. And so Here, you would test your field size, ensure that you have good settings in order to do that, and then move along to defining different flaws to make sure you can find those flaws. Here, one thing with eddy current arrays probes that is super helpful. You can test different ways of firing these probes and receiving the energy back. And depending on how you do that, you can pick up different flaws and different orientations better. So testing this ahead of time and being able to put this into practice in the actual field is very helpful. Same thing with UT, when you get phased array probes, you're actually able to simulate the delay laws that are being used for each of those elements firing, and then you can output those delay laws and load them into your equipment. And then you know your inspectors are actually using the correct delay laws or setup in order to find what they need to find. So you have assurance there as well. And then guided wave testing is used a lot in the railroad industry. And so basically what's going on here is they need to find the right mode of the wave. And then from there, they're going to look at the field coverage, similar to UT, where they can focus within the railroad track. So here you actually have the probe, unfortunately it's covered up by this image, my bad. But you have this section right here that they're looking at. And this can be utilized in underground pipes as well, because you may not want to unbury concrete in order to actually look at it. So to be able to set up a certain technique in order to test this ahead of time, to make sure it works, could save a lot of time actually digging up the concrete and the man hours that would take to do that, and then refill it all to just find out that you actually have no cracks or anything. So simulating this can be very beneficial to figure out flaw responses that you may find and from different orientations, as well as when you have transitioning and piping that can greatly affect your results as well. So figuring out what that looks like ahead of time, so when you see it in the actual test, you know that it's actually geometry and it's not a defect. Now, something that's super helpful, there is a lot of talk about AI and machine learning already today. Simulation software like CIVA can actually greatly benefit the industry for non-destructive testing, because you're actually able to get large data sets of simulated data and group them with experimental data to get large data sets. And if you're able to label these flaws correctly, then you can start using more machines in order to diagnose different flaws and their sizing if they're trained in order to do this. So right now, our biggest issue in the non-destructive testing field for machine learning is getting large data sets. And so we just don't have that, mostly because people don't want to share data. And so, which is kind of unfortunate, but simulation can help with this. And you can see here that you can study a lot of different cases, not only for machine learning, but also to predict your best and worst case scenario. And then study those influential parameters. So you'll know going into the inspection, okay, if my defect moves, if it's in this area, I'm going to be less likely to pick it up. So maybe I want to change my calibration or change something a little bit to make sure that that inspection of that area is going to be reliable. And then model-assisted probability of detection. Who knows, who's familiar with probability of detection studies, Elizabeth? Okay, awesome, cool. So I get to get trained on this next week, so I'm really excited. And get like really into the nitty-gritty of non-destructive testing probability of detection studies. And so why not use simulation to figure out how to set up a probability of detection study? In non-destructive testing, from what I have heard from some colleagues, in order to do these studies and to qualify procedures, you actually have to order these mock-ups that have multiple different flaws of different sizes, and then take multiple different people to actually try to find those flaws and identify them and get all this data together, just to take this mock-up that you ordered that was hundreds and hundreds of thousands of dollars to cut it open and make sure that the flaws are actually what they said they were, the manufacturer said they are. And so why not make sure that before you order the mock-up that you're actually going to order what you need to order by testing some simulated cases? Because I have had colleagues tell me that they have ordered calibration blocks and different things that are $400,000. just to find out that they're not going to work for their application. And so that's not a good thing. And so why not use simulation to help with this and identify uncertainties in key areas? Some future applications where simulation software for non-destructive testing can help is to actually be able to do designing for inspectability. Right now, a lot of times what's happening is the design engineers are not always aware of non-destructive testing sometimes. Sometimes there's a gap depending on the company or industry. And they design the part to make sure it's going to be able to endure the loading and the stresses that it's going to be under. And then by the time it gets created and it gets into the actual build process and it needs to be inspected, the inspectors come along or the NDT engineers come along and figure out that they're not actually able to inspect the component that was created. That's pretty bad. This can cause major delays in manufacturing schedules, major costs, because now they have to figure out, are they going to redesign this part and remanufacture it? Not normally is what happens, is that the actual NDT engineers have to figure out a new technology to actually inspect these areas, which leads to a lot of costs that they didn't predict ahead of time. And so this could be very, very helpful to be able to feed information to design engineers. Yes, your design's inspectable, or no, it's not, based on simulation, and tell them what may need to change in order to allow for it to actually be inspectable. So you don't have those manufacturing schedules being interrupted when your customer's waiting on your aircraft carrier or submarine or airplanes. And this is really important because some of our infrastructure is old. And so we want to make sure that we do this ahead of time so that we don't have delays later on when we actually need these different components and vessels. So there's a couple other ones, but I'm not going to go through them for the sake of time. But thank you for listening to my formal presentation. This concludes it at this time. If you have any questions, I'd be happy to address them.
I have a question. When you do your signal processing for the ultrasound data, do you at any point use the wave equation to get a high resolution image?
Are you talking about accuracy parameters for the model itself? Or are you talking about Snell's law and things like that?
Well, so you know what the wave equation is? It's a differential equation that dictates how waves propagate.
Okay.
Well, for example, in seismic data processing, you can use that to get a high resolution 3D image of the.
Right.
I was wondering if you all do something similar for ultrasound.
So the way the models are going to be calculated in this case, the different waves and how they propagate, is using semi-analytical models and different algorithms. There is some finite element models that are actually being hybrid approached here, and then they're working on full finite element, but it's a kind of go between computation time and accuracy. So if they're able to use semi-analytical models, they're a lot faster to run and compute, whereas finite element takes a lot longer. And so there's kind of this hybrid approach going on to make sure we're able to cover vast components and more complex situations. Did that answer your?
Yeah.
Okay, cool. Yes.
So the purpose of your simulations are to calibrate the actual sensor you're going to use for the real testing?
So you can use simulation to help you calibrate, especially for figuring out delay laws for your phased array UT probes. But a lot of times what it's used for is to make sure the technology you're using. So for UT, you have single element, dual element, phased array. Make sure even within phased array, you can focus many different ways. Make sure that whatever you're using is actually going to be able to detect what you need to detect in terms of crack size or porosity and different things like that. Does that?
Well, I think it's going in the direction I think it is, but let me just double check.
Yeah.
So, you mentioned submarines and aircraft carriers, and we got all these welds. And we have to do 100%.
Right.
checking. So you're not doing simulation on the welds, but you're doing simulation on the equipment that, or on the technology that's
Right.
gonna actually do the non-destructive testing.
Right.
And the purpose of that is to make it so the parameters, when you're doing the real testing, have the best chance for success.
Correct. So yeah, you would try to accurately model that weld with the different grain structures. PNNL, I believe, did like a 10,000 volume grain structure weld and simulated it in CIVA. So you can make your models pretty advanced, like you said, for those welds, and then text the different parameters and whatnot, yeah, for that application.
One more
Yeah.
follow-up to it.
Go for it.
You had a slide, I think it was on the model assisted probability of detection, and it actually said, I think the words optimize, design, and experiment.
Yes.
So are you using statistically designed experiments to run the fewest simulations to determine what are the optimal parameters for your testing?
Yeah, so there's something called in CIVA parametric studies where you would vary certain parameters at certain points, and then we can use statistical distribution algorithms and things to actually get a model assisted POD. So get the uncertainties in between those variations. So we have a huge data set, and then make sure that the in between values that weren't directly computed, but were done with mathematical approaches, actually line up with experimental values, and you can test to that with different algorithms or statistical distributions to ensure that your data is going to be relevant. So yes, you can cut down on your simulation time and get more and more data that way.
So I know my personal experience, interacting with you all that a couple of years ago, there was some interest in creating, machine learning surrogate models for, in order to get, a higher resolution solutions without all the time that it takes. Has that continued to develop? Have you still have people working on that?
I'm pretty sure yes, but I'm not exactly sure because I have heard about that, but I'm not sure where it's at in the development process. I would have to talk to the CEA who actually develops the software. We're just the exclusive distributors and technical support and training for the software. So sorry, great question, but I'll have to get back to you. I'll ask, yeah.